set up the live stream. Okay, it's done. And go back. All right then, let's start this. So the first question, where is it? Okay, the signal frequency of 2 megahertz. What is the period of the signal? So frequency is 1 upon, sorry, we need to find time period. So time period is 1 upon frequency, which means 1 upon 2 times 10 raised to the power 6. So let's try finding this. This is 1, 2, 3, 4, 5, 6, 7. 5 into 10 raised to power minus 7 seconds. Now minus 7 seconds, right? So if we bump it to 510 raised to 9 seconds, then we can write it as 500 nanoseconds, which is t. Pretty good. Now going to the next one. A metal sphere of radius r is dropped into tank. As it sinks at speed v, it experiences a drag force given by F equals to KRV, where K is the constant. What are the SI base units of K? Okay, so we are going to make K the subject of the equation. This is going to be F over RV. Force can be written as MA RV. So mass is kg, acceleration is meters per second square, r is the radius, right? So 1 upon meter, and v is the speed, so meters per second. So what we can do then, kg meters per second square times 1 upon meters times second over meter. Now you can cancel one of them, cancel this with this, so this will be kg, second minus 1, meter minus 1, so that's C then. Pretty good. Okay, now which physical quantity would result from calculation in which potential difference is multiplied by electric charge? Potential difference multiplying by electric charge is work done, or energy, whatever, that's electrical energy, right? Okay, this isn't hard up till now. You're saying it's hard. Okay, let's see what's ahead. Okay, so these type of questions are not going to come anymore. The reason is that they removed it. That's why you don't need to do this. It's sort of a area where we're unsure, but I don't think this is going to come anymore. But this might come. So the flywheel has a small magnet M mounted on it. Each time the magnet passes the coil, a voltage pulse is generated passed through CRO. Fair enough. And then it says that what is the time base display clearly separate pulses on the screen. Okay, fine. So we have 300 revolutions per minute. So 300 over 60 would be the frequency. So 3000 divided by 60 is 50 hertz. 50, the time period will be 1 upon 50, which is 1 divided by 50 is 0.02 seconds. Now then we got to do time equals to time base times the wavelength, right? Displayed, or the length displayed that we need. Okay, so what you do now, this is the screen is 10 centimeters wide. Okay, and if it is 10 centimeter wide, this means that we got to do something. So we have 0.02 here, and the length, the total length that we have is 10. Okay, so we're going to leave this. We're going to try setting up, like we can use these, right, to check if it basically is less than 10 centimeter, or if it's not too less or too like it's too large or too less. We have to check that. So first of all, I will check this. So if I divide 0.02 with 1, I will get 0.02 centimeter. Now 0.02 centimeter means that the wave will be like this. So it won't be very clear, right? So this can't be the answer because it will be too small to view. That's why. And then you could look at 10. So let's see, if 10 milliseconds, right? So 0.02 divided by 10 times 10 raised to minus 3. So let's try doing this. Let's pull it here. 0.02 divided by 10 times 10 divided by 10 raised to power minus 3. So this is 2 centimeter. 2 centimeter means that on this screen almost like 5 waves can be displayed. So which is this could be one answer. Let's try 100 now. So 0.02 divided by 100 times 10 raised to power minus 6. So 0.02 divided by 100 divided by 10 raised to power minus 6. This is 200 centimeter would be one wave, which cannot be displayed. So this is also wrong. 1 microsecond, let's try to do that as well. 1 times 10 raised to power minus 6. So 0.02 divided by 10 raised to power minus 6. That is like 20,000 centimeter, which is also not the correct answer. That's wrong. The only answer that makes sense is B, because it will be clearly displayed. These are too large, this is too small, like that. All right, now let's move forward. Strange, where did I put my water? Oh no. Okay, you guys gotta wait. I put my water somewhere else. All right, I'm back. Now, going to the next question. It says a fixed quantity x naught is measured many times in experiment. In experimental uncertainty, graph is plotted to show the number n times. Fine. Which graph could obtain if the x is, it has large systematic error but small random error? Large systematic error means that if this is the original value, it will be like shifted away from it. So neither this answer is correct, neither this answer is correct, because the peak is exactly at the true value. So peak needs to be shifted, okay? Which means C and D might be correct, but the peak is shifted. But because it has small, it's a small random error, which means that the spread will be small as well, which makes sense because here the spread is smaller. So C has to be the right answer there. All right. Now, going to the next question. So a ball is thrown horizontally and the ball is affected by air resistance. What happens to the horizontal and vertical components of the ball? So air resistance not only will affect the vertical component, but it will also affect the horizontal component. The horizontal component will basically has to decrease to 0 because air resistance opposes it. The vertical value will actually, because initially it will be 0, but as it falls down like this, the vertical velocity will increase, but it will reach terminal velocity, so it increases to a constant value, has to be p. Right. Constant rate and constant value means rate of velocity is acceleration, so it does not increase acceleration to a constant value. It's just like it is there, right? So it will go down and become 0. Now a stone is thrown up at time 0. Area x represents a distance 5 meter. Area y represents a distance 3 meter. What is the displacement of stone from the original position? So it will be 5 minus 3, and this will be 2. So that has to be A, because displacement is a vector quantity. You have to subtract it. They're like, this is minus, this is positive. Now in order that a train can stop safely, it will always pass a signal showing a yellow light. Okay, so there is a yellow light, and then reaches a signal showing red light. Drivers apply brake at yellow light, and the result in uniform deceleration and stop exactly at red. Okay, the distance between red and yellow light is x. Okay, and then it says what must be the minimum distance between lights if the train speed is increased by 20%. An increase of 20% means 20% is basically 20 divided by 100, which is 0.2. So increase would be, if the let's suppose the speed was 1, so increase would be 1.2. So the new speed would be like this, right? 1.2 of the old speed. So let's say old speed was u, the new speed will be 1.2 of u. Now it says without changing the deceleration, how will the